In the span of just 5 months, two brand new aircraft, ostensibly the pinnacle of modern aerospace engineering, plunged from the sky, claiming 346 lives. The initial shock quickly gave way to a chilling question: how could such a thing happen twice? For an industry built on layers of safety and rigorous testing, these twin tragedies represented an unprecedented failure, shattering public trust and raising fundamental questions about the very foundation of modern aviation. This wasn't merely a coincidence, it pointed to a deeper, more insidious problem within the design, certification, and operation of Boeing's new flagship jet. While initial reports often lean towards pilot error in complex aviation incidents, the striking similarities between the two crashes immediately suggested a systemic root cause. This wasn't about individual mistakes in the cockpit, but rather a confluence of factors deeply embedded in the aircraft's design, its certification process, and the training provided to those who flew it. We're talking about intricate software systems, regulatory blind spots, and the profound pressures of a highly competitive global market. To understand the true reason, we must dissect each layer, moving beyond the superficial to the structural vulnerabilities that led to disaster. Boeing's decision to develop this new plane wasn't born from a blank slate but from intense market pressure. Rival Airbus had launched its highly successful A320neo, boasting significant fuel efficiency improvements. Boeing, facing a potential erosion of its market dominance, needed a swift, cost-effective response. The imperative was clear: deliver a competitive, next-generation aircraft quickly, without incurring the massive expense and time associated with an entirely new design. This commercial urgency set the stage for crucial design compromises that would later prove catastrophic. Instead of a clean-sheet design, Boeing opted to modify its highly successful, decades-old airframe. This approach promised significant advantages: reduced development costs, faster certification, and minimal retraining for pilots. However, the larger, more fuel-efficient engines required for the new plane didn't fit easily under the existing wing. They were mounted further forward and higher, altering the aircraft's aerodynamic characteristics. This seemingly minor change introduced an inherent tendency for the aircraft's nose to pitch up, particularly at high angles of attack, threatening its stability and potentially leading to a stall. To counteract this new aerodynamic characteristic, Boeing introduced the Maneuvering Characteristics Augmentation System, or MCAS. This automated flight control law was designed to subtly push the aircraft's nose down if it detected an excessively high angle of attack, thereby preventing a potential stall. Boeing intended for MCAS to operate transparently, making the modified aircraft fly exactly like its predecessor, thus avoiding extensive and costly pilot retraining. It was an engineering solution intended to mask an underlying aerodynamic truth, aiming for seamless integration and reduced operational complexity for airlines. The critical flaw in MCAS wasn't its intent, but its implementation. It was designed to activate based on input from just one of the aircraft's two angle of attack (AOA) sensors. If that single sensor provided erroneous data, MCAS would repeatedly command the nose down, regardless of actual flight conditions or the pilot's inputs. Furthermore, the system was given significant authority over the flight controls, capable of overpowering pilot efforts to correct the trajectory. This single point of failure design choice, combined with its substantial control authority, created a catastrophic vulnerability. On October 29, 2018, Lion Air Flight 610 took off from Jakarta. Moments after departure, a faulty AOA sensor began feeding erroneous data to the aircraft's systems. MCAS repeatedly engaged, forcing the plane's nose down. Despite the pilot's desperate struggle to regain control, wrestling with the flight stick for critical minutes, they were unable to override the persistent automated commands. The aircraft ultimately plunged into the Java Sea, killing all 189 people on board. It was a terrifying, textbook illustration of the MCAS vulnerability, a stark warning that went tragically unheeded by all responsible parties. In the immediate aftermath of the Lion Air crash, Boeing and the FAA focused on a software update and a bulletin reminding airlines about existing procedures. Critically, the full extent of MCAS's power and its single point of failure design was not widely communicated, nor was the fleet immediately grounded. Boeing stated it had already been working on a software patch, suggesting the issue was known, but the urgency of the situation was severely underestimated. This hesitant, piecemeal response effectively left hundreds of identical aircraft, with the same potential flaw, in active service globally. Just 5 months later, on March 10, 2019, the world watched in horror as Ethiopian Airlines Flight 302 crashed shortly after takeoff from Addis Ababa. The flight profile was chillingly similar to Lion Air 610, a faulty AOA sensor, repeated nose-down commands from MCAS, and a desperate, futile struggle by the pilots. This second catastrophe, claiming all 157 lives on board, exposed the profound failure of the previous response. It underscored that the issue was not isolated to a single airline or region, but was a fundamental, unaddressed vulnerability in the aircraft's core systems, demanding immediate global action. A critical component of the disaster was the pilots' lack of awareness about MCAS. Boeing, aiming to minimize training costs and ensure a smooth transition for airlines, did not explicitly detail MCAS in the flight manuals or require specific simulator training. Pilots were largely unaware of its existence, its purpose, or its immense authority over the flight controls. When faced with an activated MCAS, they followed existing emergency procedures for runaway stabilizer, but these were insufficient to counteract the repeated, powerful nose-down commands. The gap between design intent and operational reality proved fatal. The role of the Federal Aviation Administration, FAA, also came under intense scrutiny. Due to budget constraints and long-standing practice, the FAA had delegated significant authority to Boeing itself to certify many aspects of its new aircraft, including safety-critical systems like MCAS. This organizational designation authorization model, while efficient, created a conflict of interest, essentially allowing Boeing to certify its own work. Reviews after the crashes revealed that the FAA's oversight during the MCAS certification was inadequate, missing critical details about its design and potential hazards. This delegation proved a significant regulatory blind spot. Beyond technical failures, investigations unearthed a concerning shift in Boeing's corporate culture. Historically an engineering-driven company, a heightened focus on financial performance and aggressive production quotas began to overshadow its legendary safety-first ethos. Employees reported immense pressure to accelerate production and cut costs, potentially compromising rigorous safety reviews and open communication about design flaws. This cultural pivot, from prioritizing engineering excellence to financial metrics, created an environment where critical warnings might have been downplayed or overlooked, contributing directly to the tragic outcome. Modern aircraft are as much software platforms as they are mechanical marvels. The new plane incorporated millions of lines of code, managing hundreds of interconnected systems. MCAS, though a seemingly small addition, had deep interdependencies within the broader flight control architecture. The complexity meant that changes in one area could have unforeseen consequences elsewhere, making thorough testing and validation paramount. The investigations highlighted that the software's interaction with a single, faulty AOA sensor was not adequately modeled or tested under real-world, abnormal conditions, a testament to the challenge of predicting every failure mode in highly complex digital systems. The second crash triggered an unprecedented global grounding of the entire fleet, lasting 20 months. This action, driven by regulators worldwide rather than the FAA initially, cost Boeing an estimated $20 billion in losses, compensation, and production halt charges. During this period, Boeing undertook a comprehensive redesign of MCAS, incorporating inputs from both AOA sensors, adding redundancy, and providing pilots with the ability to override the system more easily. New pilot training requirements were also mandated, including simulator sessions that specifically addressed MCAS malfunctions. It was an arduous, costly, but necessary path to regaining public and regulatory trust. The tragedies prompted a profound reassessment across the aviation industry. Regulators globally vowed to strengthen oversight, reduce reliance on delegated authority, and enhance scrutiny of software-driven systems. Boeing itself committed to a renewed focus on safety and transparency, overhauling its engineering processes and corporate structure. Pilot training standards for highly automated aircraft are also being redefined, emphasizing a deeper understanding of underlying systems rather than just memorized procedures. The goal is to ensure that technological advancements enhance, rather than compromise, the fundamental principles of aviation safety, ensuring such a dual disaster never recurs. The real reason Boeing's new plane crashed twice was not a single point of failure, but a catastrophic interaction of multiple systemic vulnerabilities, a design choice that introduced aerodynamic instability, an automated system with excessive authority relying on a single sensor, insufficient pilot training and awareness, and a regulatory framework that fell short on oversight. Layered beneath this was a corporate culture seemingly swayed by production pressures. The human cost is immeasurable, but the indelible lessons learned must forever reshape how aircraft are designed, certified, and operated, ensuring that safety always remains the paramount consideration above all else.